Okay. So again, once again, welcome to the fresh session today. We are starting Unit 2 today. So the title of Unit 2 is Distribution and Density Functions and Operations on One Random Variable. Okay, so here mainly we'll be focusing on single random variable. Okay, so we associate a single random variable for a particular experiment, and then we define some mathematical operations on that, and we study its properties and how it is useful practically. Okay. And today's title is the first topic, that is distribution and density functions. So we are getting introduced to distribution and density functions. So this is the outline of today's session. We'll be seeing what is a distribution function and see what are its properties. Again, we'll be seeing what is a density function and its properties. Okay. Yeah. So now consider this was the first slide in our previous session, right? So we saw how a particular sample space can get itself associated with a set of real numbers in the number line. Okay, so we defined a particular experiment where we are picking a random student. Okay, so there are some students in a class. Maybe we are selecting students for a particular tournament or a particular exam or a competition. Okay, so each student is the outcome of that experiment. Okay, so maybe student S1 is an outcome of this experiment. S2 is a particular outcome. S3 is a particular outcome. Okay, so the student or the name of the student is just a quality. Okay, so we are associating a number with the student by following certain rules. The rules are like, the first rule was that we are just measuring the height of the student and associating a number with him. Okay, the height is the number associated with the student. In the second case, we associated weight. Okay, that weight as the number that gets associated with each student. Okay, similarly, we define also height in centimeters. Okay, so these are different kinds of methods or rules that we followed to associate numbers with the outcome of a random experiment. Okay, fine. So now we just associated some number with the outcome of an experiment. If you remember the previous lecture, like if you remember the initial concepts we studied, there are 3 steps in modeling an uncertain situation, right? So the first step is to define a sample space. The second step is to identify some events in the sample space. And the third step is to assign some probabilities, right? So initially we are just allocating some probabilities for each of the events. Okay, so now how to bring the probability picture into this random variable? Like we said that a random variable is a tool to mathematically analyze uncertain situations. Now how to bring the probability picture into the random variable domain? Like how to associate? Now we know that everything in this line is a random variable, right? So that is the numbers that the rule results, like whatever rule we follow to find out the number. So these are the numbers which are the result of following certain rules and assigning the numbers, right? So how do we bring probability? So these numbers are not probabilities, right? So these are numbers associated with each of the outcomes. So this is the number associated with this particular outcome. Okay. So how to bring probability? So we have to somehow associate a probability to this value, and each of the value on this number line, right? So that association of this probability is done by 2 methods. One of the method is what is known as a distribution function. Okay, so defining a distribution function is one method of bringing in the probability picture into the domain of random variables. So there is one other method which is known as the density function, which we'll be seeing later on in this session. So first we'll define what is a distribution function, and then we'll introduce what is a density function. Okay, so now, so to understand the concept of this distribution function, just consider this probability. Okay. So consider this probability, that is probability of the random variable h being less than or equal to h1. So how can we find out that probability? So h1 is located here. Yes. So this denotes the probability of some event, right? So what is that event? It is the event h less than h1. Okay, so the capital H denotes the random variable. That is the steps we follow. Okay, so random variable is not random. It is not a variable, right? It can be considered as a subroutine. Like if you are aware of programming, so in programming we say there are some functions and subroutines, right? So the capital H represents a subroutine where it is a collection of some steps to follow. Okay, so the capital H represents a subroutine, and the small h denotes the results of the subroutine. Okay, so what does this mean? So in what does the quantity inside the curly brackets mean? Right. So it just represents an event. Okay, what is the event h less than h1? So now come back to the sample space. What is the event h less than h1? Is anyone? What is the event h less than h1? So h1 we know it is located on this number line. So from this number line we again go back to the sample space. Okay, so less than h1, what are the numbers available? We have this h3, that is 71.35, and h4, right? So we might have some numbers here. Maybe we're not shown some other students. Maybe there are some students here, like S5, S6, etc., who might have some values associated with them which are located here. Okay, but we'll consider only the values that are shown here. Okay, so h1 is corresponding to S3. Right, so h3 is corresponding to, sorry, h1 corresponds to s1, and h3 corresponds to s3, h4 corresponds to s4. Okay, so what is this event then? H less than h1, it is nothing but the subset which includes s1, s3, and s4. Okay, so if you are selecting the group of these three students, then we say event h less than, that is capital H less than or equal to h1 has occurred. Okay, so this is how we are moving from the domain of the real numbers to the domain of our sample space. Okay, so this is the particular event, and that is the probability of that particular event. Okay, so this is the subset of the sample space. Okay, so which is represented by this event. Okay, so it is represented by this event. Okay, so now we are asking the question, what is the probability of that particular event? Okay, what is the probability of that particular event? Yes, what is the probability of h being less than h1? Just recall your previous concepts about probability. So we have three outcomes which contribute to this event. Okay, so then it is nothing but it is the sum of all the three outcomes, right? So it is the sum of capital H being equal to h4 plus capital H being equal to h3 plus capital H being equal to h1, right? So it is the sum of the probability of all the three things. Okay, we are just going to add these three probabilities. That is the probability of capital H being equal to capital H being equal to small h4, h3, and h1. Okay, so if we add these three probabilities, so that will lead us to the probability of this particular event, right? So I have just defined or I have just introduced this concept for one particular h, one particular small h, h1. Okay, so similarly we can consider probability of the capital H being less than or equal to h3, or the probability of capital H being less than or equal to h4. Okay, I can ask the same question at any point on the number line, right? At any valid point on the number line. I can even ask the question standing here, right, at h2. So capital H being less than or equal to h2. So that will include all the probabilities, including h2, right? So it will start from here, and so all through this we have to sum up all the probabilities up to h2 when here h2 is given, right? So when capital H being less than or equal to h2 is asked, we have to sum up all the probabilities that are to the left of h2. right? Suppose if I ask the question here at H3, so we'll be adding just two, this one and this one. Okay, so this, if you just observe this probability, it is a function of the location of the small h1, right? It is the probability that results when we do the calculation. It is a function of the point where the small h is located, right? So we can very well convert this into a function of h. Okay, so we'll just do that in the next slide. Okay, so this is just again the same concept. Okay, so we just asked the question, what is the probability of getting the capital H less than a particular small h, right? So and then we observed that each whenever we ask each such question, it is a function of where that small h is located. So we move on to define a function which is has an argument of the small h, and then we call that function a distribution function. Okay, so now we formally define what is a distribution function. Okay, so given any random variable x, the probability that is capital X less than or equal to a particular small x denotes the probability of the event capital X being less than or equal to small x. Okay, so it is a function of x denoted by capital Fx of x. Okay. So I hope you are understanding the concept what I'm trying to introduce. Okay, so just now in the previous slide we saw the value of this probability depends on the location of this x. Okay, so that is why for our convenience we are defining a function Fx of x. Okay, so we are extending our concept of individual probability to that of a function. Okay, to that of a continuous function Fx of x. Okay, so here you notice, you observe the notation. So the suffix is capital X and the argument is small x. Okay, so this Fx of x denotes what is called the distribution function of the random variable x. Okay, so what is the use of this function? So it just helps bring the probability picture into the domain of random variables. Okay, so there are other names for the function. So we also call it the cumulative probability distribution function. Okay, so this is a very elaborate name given to that function, but usually when in our discussions we'll be simply stating it as a distribution function of the random variable x. Okay, so how is it defined? It is nothing but the probability of x being less than or equal to x. Okay, so here we represent individual probabilities when x takes some particular values. Okay, as a general rule, we just make it as a function. Okay, when x can take any value, we create a function Fx of x. Okay, so notice the capital F. Okay, so all the distribution functions are denoted by capital letters. Okay, so density functions will be denoted by small letters. Okay, so you have to be thorough with the notation so that we can avoid confusions later on. Okay, so most of the things in this chapter will be based on some notations. Okay, so please focus on the notations and avoid mistakes later on. Okay, again, this x can take any value from minus infinity to plus infinity. Since x is the real, it is a number that is taken from the real number line. So it can take values from minus infinity to plus infinity. Okay, so what we have done is we have initially considered the probability of individual points on the number line, and then we extended that to that of a function, that is Fx of x, and we named that function as a distribution function of x. Okay, so now we'll see some small example. How does a distribution function look like? Okay, so what is the general what do you call general schematic view or a diagrammatic view of the distribution function? Okay, so generally, how does a distribution function look like? Okay, so again we go back to our same example of choosing a student from a class, maybe for a particular tournament or something. Okay, so here you can see I have given the same number line. which I use to denote the height of the students. Okay, so now I introduced one more axis here. Right, I'll just use my highlighter. So this was our previous number line. So now I have introduced one more axis here, that is the y-axis. Yes, the y-axis represents the capital FH of H. Okay, since our random variable is already denoted by the capital H, I'm using f of capital H, and inside the brackets the argument is small h. Okay, so now I have associated some, you can see I have some values denoted on the y-axis right here, right? Okay, so what I have done is I'm using this red colored graph, right? So you can see a red graph that is going here like a staircase, right? Okay, so this particular distribution function, it is for a discrete random variable. Okay, so for example, consider our example of selecting a student. In that, assume that we have just 4 students in the class. Okay, so H1, H4, H3, H1, and H2. Okay, so now this is a case of a discrete random variable. So assume that we are eliminating this decimals here. We are just taking some integer values. Okay, and then we are saying that the probability of the students with height less than 60 getting selected is 0.15. Okay, so the probability of students with height less than 71 inches being selected is equal to 0.55. So okay, so these are the probabilities that we are denoting here. Okay, okay, so what does this red color staircase denote is, so the probability of students with height less than 60 inches getting selected is 0.15. Okay, so that is what is denoted here. So the probability of students with height less than 71 inches getting selected is 0.55. The probability of students with height less than 82 inches getting selected is 0.65. And similarly, like probability of students with height 86 inches less than or equal to 86 inches being selected is 1. Okay, so what does this mean? So when you come to the height of 86 inches, almost all the students are below that height, right? So definitely one student will be selected. So that is why this probability has become 1. Okay, so now we have a staircase function, right? So how to represent this function mathematically? Okay, so whenever we are considering a discrete random variable and bringing in the probability picture here, so we'll be getting this kind of a function, right? Will be getting a staircase function because the values here on the x-axis are discrete values. Okay, so now we want to mathematically represent this staircase. So what we use a particular notation for this staircase. Okay, so we use summation I equal to 1 to n. Okay, so where n represents the total number of points on the x-axis, right? So suppose here we are just having n equal to 4 because we are considering only 4 students in the class. So here n equal to 4. So the distribution function takes the form sigma I equal to 1 to n p of x equal to xi. So observe the equal to sign here. It is p of x equal to xi multiplied by u of x minus xi. Okay, so now this function, this u is a special type of function. Okay, so we have to carefully observe this function. This u is a special type of function which is defined by this equation. Okay, so it is called the unit step function. So u of x is called the unit step function, which is defined as it is equal to 1 for the values of x greater than or equal to 0, and it is 0 for the values of x less than or equal to 0. Okay, so now you have to observe we are introducing a shift here. Okay, so we are shifting the unit step function u of x by an amount equal to xi. Okay, so what we are doing here is we are just shifting the function from origin to a particular point xi. Okay, so now we'll take a brief diversion from this slide. I'll just teach you a little bit more detail about this unit step function u of x. Okay, so I'm just coming out of this PPT. Just want to I just want you to observe this unit step function. Okay, so yeah. So are you able to see my screen? See the PDF? I'm just going full screen. Yeah. So what we have here is the unit step signal. Okay, so here we are considering we are saying them as signal, but you can very well say it as a function. Okay, so it is defined as it is equal to 1 when, so it is u of t. So previously we saw u of x. Okay, so the independent variable is changed to t here. So u of t equal to 1 for t greater than or equal to 0, and it is 0 for t less than 0. Okay, so this is a special function which is called a unit step function or a unit step signal. Okay, so this is how it looks. So this is how a u of t or u of x looks. So if there is x here, we denote here by u of x. Okay, so it is a function which is like a single step at 0. Okay, so that is what is the unit step function. Okay, when you make a shift in t, that is when the t inside this unit step is changed to t minus t naught. What happens is the function shift to another place. So suppose here we have t naught, so the entire step is shifted to that value. Okay, so just I wanted to convey the meaning of what is a unit step. So hope you understood what is this function denote. So anyone having any doubt here? Is the concept clear? See, if you plot this function, you'll be getting a function like this. So this is the x-axis. So you'll be getting a function which is 0 for all time before 0. So when x equal to 0, it starts and becomes like a staircase. Okay. So when x equal to xi, so if we are using this function u of x minus xi, so suppose assume that xi is here. Okay, so this is our xi. So what happens is this function shifts to that particular place xi. So it just becomes like it is 0 for all the values below xi, and at xi it rises and becomes 1. Okay, so this is the value of 1. Okay, so this is called a unit step function. This is the shifted version of unit step function. So what we are basically doing here is we are shifting the unit step function to locations where our different heights are located. Okay, so to the places where our different height values of the students are available. Okay, so here we are making one unit step function. Okay, so one more unit step function is added here. Okay, one more unit step is added here, and one more here. Okay, so this red colored graph, it just represents the sum of, so already there is a unit step function here. So on top of that, we are adding one more step here. So that is represented by this red line. Okay, already there is a unit step function here. On top of that, we are adding one more small step. So that brings us to this level. And again, from this level, we are adding one more step. That brings us to this level. Okay, so it is a cumulative sum of many shifted unit steps. Okay, the height of the unit steps are formed by the probability values of the random variable x. Okay, so the h4 has a probability of say 0.15. Okay, h3 has a probability of say 0.35. right? It's yeah, it is 0.3, I think. Yeah, so 0.15 plus 0.3 is 0.55. Okay, so this height, it represents the probability of this particular h, small h. Okay, again this height, so the height from this level. Okay, so this height represents the probability of h2. So similarly, this height, okay, this represents the probability of h1. So this height represents the probability of h2. Okay, so this is the notation we use to represent the distribution function of a discrete random variable. Okay, so we'll be seeing this notation in more detail in problems. Yeah. So if anyone didn't understand this concept, you can just inform me now itself. Okay, so I assume that you have understood the concept. You understood the concept of especially this u of x. Okay, which is called the unit step function. Okay, so for the continuous random variable,
Excuse me, sir.
yeah, please, yes,
Excuse me, sir.
yeah, tell me.
Sir, I joined yesterday on itself, so I am having some difficult.
Okay. Your name is uh,
Lal
yesterday I got
Meher.
a Lal Meher. Okay.
Yes, sir.
Okay, so yeah, you will be finding little bit difficult regarding these concepts. You can mail me your questions. Okay. So, do you
Okay,
have my
sir.
mail ID?
No, sir, I don't have anything.
Okay. You can contact the class representative. So she'll be giving you the mail ID. Okay.
Okay, sir. Sure.
Okay. Yeah. So anyway, even if you don't understand the previous unit, you can start from this unit also. Okay. So in a previous unit's material, I'll be providing you. So
Okay, sir.
you can start observing the class from this unit. Okay. So these concepts
Okay,
are
sir.
very basic concepts. Okay. So what we are introducing here is just two different functions. Okay. So the name of the function is distribution function, and we are relating probability with a particular function in a real number line. Okay.
Okay,
Okay.
sir.
So you can ask your doubts in the mail. Okay. I'll be helping you in the mail.
Okay, sir. Thank you.
Okay. So I'll proceed with the class now. So okay. So now considering previously we considered the distribution function for discrete random variables, right? So discrete random variables just occupy some discrete points on the number line, right? So now we are talking about continuous random variables. So as the name suggests, the random variable is defined in all the points along the number line, right? So we have legitimate random variables or legitimate points or valid points at all locations on the number line. Okay, so that is why we give the name continuous random variable. The highlighter. Okay, so all the points along the line, this line, have some associated event in the sample space, right? So that is why we call them as continuous random variables. Okay, so there is a stark difference between the distribution function, the form of the distribution function in the discrete random variable case and in the continuous random variable case. Okay, so here the functions are continuous functions, so there are no staircases, right? So in the previous slide, if you see, so here we have all staircases, right? So there is one step here, another step here, another small step here, and another step here. Okay, so all these are staircases, but in this case, all are smooth functions, right? So there is no discontinuity. Okay, so the staircases, so the other name for staircases are discontinuity. Okay, so what do you mean by discontinuity? So just below h3, for values which are less than h3, the value is at 0.15. So for values greater than h3 immediately the graph jumps to the value of 0.55. Okay, so these are called discontinuities or jumps. It is also called staircases. Okay, so all these vertical lines, okay, so these are called discontinuities in the function. Okay, so here in the continuous random variable case, we don't have any discontinuities. All the functions are smooth functions. Okay, so I've shown different functions, different colors. So the blue colored one represents a particular function. Okay, red colored one denotes another particular function. Okay, so all these are not associated with the single random variable. Okay, so these are associated with different random variables. So this is for different variable, this is for a different variable, this for another variable, this for another variable. I just want to show different types of smooth graphs. Okay, so these are the things we should note about distribution functions of discrete as well as continuous random variables. So discrete distribution functions will always have staircases. Okay, continuous random variables will always have smooth graphs. Okay, so if you observe one more thing in the graph of distribution functions, so all the distribution function starts at a value of 0, right? So on the leftmost corner, bottom leftmost corner, the functions are starting at a value of 0, and they're doing some kind of variations here, and then finally they are reaching a value of 1, right? So if you observe the previous slide also, here also we can see it is starting at a value of 0. So here it is doing some staircase thing, and then finally it is reaching a value of 1. Okay, so this is a general characteristic of a distribution function. So always it will start from 0, and at the rightmost end it will end up with a value of 1. Okay, so all these things we are consolidating into a list of properties of distribution functions, which I denote here. Okay, so these are the properties of important properties of distribution functions. Okay, so the first there are some 6 properties. So the first property says that at minus infinity, okay, so at the value of minus infinity for the random variable, the value of distribution function is 0. Okay, so what does minus infinity mean? So at the leftmost side, that is we are seeking probabilities which are less than minus infinity, right? So most of the time that doesn't have any corresponding event in the sample space. Okay, so that is an impossible event, so that's why we are getting a value of 0. Okay, and then fx of infinity equal to 1. So what do you mean by that? It is the probability of all the events that correspond to the random variable being less than positive infinity. Okay, so that, what does that denote? It just denotes the entire sample space, right? So on the number line, positive infinity denotes the last value that a random variable can take. So any value below that last value will definitely have some event associated with it in the sample space. Okay, so definitely this event will happen. This is a sure event. So this becomes 1. So okay, so the distribution function takes a value of 1 at positive infinity of the random variable. Okay, and then this is again a result of our basic probability axiom. So the value of the distribution function will be always greater than 0 and less than equal to 1. Okay, this is because all these are probabilities, right? The distribution function is also a kind of probability, right? It is the sum of all probabilities. So definitely its value will be within 0 and 1. So that is what is the third property. And then here what we are seeing is fx of x1 is less than or equal to fx of x2 if x1 is less than x2. So what does this mean is, so the distribution function is always an increasing function. So that is what is given by this property. So since probabilities always add up, either they remain constant or they add up. Even if the points that are to the right side of the graph, they are having very small probabilities, they will add up to the previous probabilities. Okay, so what happens? Always the graph is increasing towards the right side. Okay, so always the graph goes up when you move from left to right. Okay, so when you move from left to right along the number line, so the graph is always increasing. Okay, so that is what is denoted by the fourth property. So any distribution function will have a graph which is always increasing towards the right side. Okay, so there is a fifth property. Okay, so the probability of the random variable being greater than x1 and less than or equal to x2. Okay, so that is the probability of our random variable lying between two limits x1 and x2. Suppose this is x1 and this is x2. Okay, so x1 may have some probability here, right? X2 will have some probability here. So the graph may take some different shapes to reach from here to here. Okay, it may take like this or like this. Okay, so this cannot be possible because always increasing, so it can take any different shape. But what we are getting is the probability that our random variable lies within these two limits is nothing but the difference of this probability and this probability. Okay, so that is what is given by fx of x2 minus fx of x1. Okay, so the probability that our random variable lies between the value of x2 and x1 is nothing but the difference of this probability and this probability. So that is this height. Okay, so this height represents the probability of a random variable lying between these two limits. Okay, so this is a special property of the distribution function. Okay, and then the final property says that the distribution function is continuous from the right side. Okay, so sometimes when you have a staircase, you can have like staircase like this. Okay, what it says is the function is continuous from the right side. So if you are observing points which are close to the staircase nearby here, so you'll have same value. Okay, so at any discontinuity, it is continuous from the right side. So fx of x plus is equal to fx of x. So we'll see this property in more detail when we do some problems. So for now, we can understand that any distribution function is continuous from the right side. So it is called right continuity. Okay, it is continuous from the right side. So that is what it means. Okay, so we'll be doing problems based on these properties. So we'll be assessing whether a particular function can qualify as a distribution function or not using all these properties. Okay. Now moving on to the density functions. So these are the types of distribution functions we'll be seeing in both the discrete case as well as in continuous time case. Sorry, in continuous random variable case. Okay. Now we define what is known as the density function. Okay, so a density function is defined using the distribution function as its derivative. Okay, so what we are basically defining is, so we are defining what is called a density function. It is nothing but it is a derivative of the distribution function. Okay, it is denoted by small fx of x. It is nothing but the derivative of the capital Fx of x. Okay, so and then again the density function is also a very useful tool in mathematically modeling our probability problems. Okay, so it increases our efficiency of solving the probability problems by using a lot of mathematics and calculus. Okay, so these are the properties of density function. So as we had properties of distribution functions, we have a density function satisfying all these properties. So the value of density function is always positive. Okay, so if you are seeing this as the derivative of fx of x, so in the previous case we saw that the capital Fx of x is always an increasing function towards the right. Right, so if it is an increasing function, what is the slope of that function? Yes, just recall your calculus classes. So what is the slope of a function that is always increasing? Is it negative or is it zero or is it positive?
Positive.
Positive.
Okay, suppose if you have a straight line like this on the coordinate system. Okay, so what is the slope of this straight line?
Y equals to m.
1.
Anyone, please? What is the slope of this straight line?
M equal to 1.
Suppose I say it has at value x value equal to 1, it has a y value equal to 3. So what is the slope? slope equal to 3, right? So it is the difference of y coordinates divided by the difference in x coordinates, that is the slope. Okay, so any function which is always increasing towards the right will have positive slope, right? So that is what is denoted by this property. Okay, so all the density functions will be positive, always greater than 0, because they are slopes of the distribution functions. They will always be positive because distribution function is always increasing, right? Okay, so and then this is another important property of the density function, which says that the integral of the density function over an infinite interval is equal to 1. Okay, so this is again a restatement of our probability rule. So if you add up all the probabilities of the events in the sample space, what you get is a 1, right? So all the probabilities in sample space add up to 1. So that is what is denoted by this property. Okay, so the density function, when you integrate the density function, finally what you get is a 1. Okay, and then what is the third property? So it is the reverse of this definition. So we have defined it as the derivative of the distribution function. So we are just inverting the definition and saying that the distribution function is the integral of our density function. Okay, so these two are just reverse of each other, right? So here what we are saying is the density function is the derivative of the distribution function. Here what we are saying is the distribution function is the integral of the density function. So only difference is we have introduced a different integration variable here. Okay, so the variable of integration is zeta. Okay, but in the limit we have minus infinity to x. Okay, so whenever we compute the integration, finally for the wherever zeta occurs, we are just substituting the value with x. So this will become a function of x, which is denoted by fx of x. Okay, so and then what is the final property? It says that probability of the random variable x lying between two numbers x1 and x2 is nothing but the integral of the density function between those two numbers. Okay, so whenever we have a probability distribution function, so if you have a density function like this, some kind of a density function, so we want to calculate the probability of x lying between these two limits. Okay, so these two limits, so you just have to calculate this area, so area of this shaded region. Okay, so this area is given by the integral of fx of x between x1 and x2. Okay. Okay, so these are the this is how we define the density function, and these are the properties of density function. Okay, so till now we have defined two functions. One is the distribution function and the other is the density function. Okay, so both these functions are very useful tools while doing practical probability problems. Okay, so these are very useful mathematical tools for solving probability problems in a very efficient manner. So that is why we introduced two different functions. Okay, so when we consider density functions, we say that it is the derivative of the distribution function. We'll see how does the density function look like. Okay, so if you say if you have a distribution function which is in the purple color, okay, so this is how its density function will look like. Okay, so the dashed purple line represents the density function. Okay, so what does it represent? It represents the slope of this purple line. Okay, the continuous purple line has a slope which is equal to maybe say 1. Okay, so here when the function is starting, we have a slope of 1. Okay, similarly I have also shown another graph which is in green color. So how does the slope of that graph look like? See, derivative is nothing but slope. Okay, so we are calculating slope at every point on the graph, right? So that is what is the meaning of derivative. So how does that look like? So for the green one, so you can observe here is the highest slope, right? So the slope is increasing at a rapid rate at this point. So here we'll have a peaking of the density function, right? So how does it look like? It will be looking like this. So here it will have a most highest peak, and then again it will reduce to 0. Okay, so here in this region, if you see, the slope again reduces to 0. So the curve flattens off, right? So here the curve is almost vertical. Here again it is very flat. Here extremely flat. Here it is vertical. Here it is almost flat. So that is why the function The derivative of the green graph is represented by the red colored graph. The derivative gets a peak here and then it just dies down here. Okay, so it just becomes 0 at this point. So this when it is flattening off, it becomes 0 here. Okay, so these are the general forms of the density function. So if you have a density function which is the derivative of the distribution function, we can plot different graphs which are real-time derivatives of these functions. So for continuous random variables, this is a very simple case, right? We are just taking the derivative. Okay, so when you're dealing with continuous random variables, it is a derivative. But what about this kind of graph? So we have a distribution function which has a graph which has a lot of staircases. Okay, so is the derivative defined for a staircase? See, what is the requirement for derivative? So if we want to take a derivative of a function, so one important requirement is that the function should be a continuous function, right? So if you see these points, these are like discontinuities. They are called jump discontinuities, right? So how do we describe a density function for this kind of a distribution function? Okay, so since we have a lot of staircases, if you observe these points, I'm just circling those points. Okay, so if you observe these points along the graph of the distribution function, okay, this is the graph of distribution function. From this, we have to arrive at the graph of the density function. But what difficulty we face is we have a lot of discontinuities, right? So how do we find the slope of discontinuities? So if you observe carefully, the slope is infinite here, right? So it is like climbing a mountain in a vertical fashion, right? So the slope of mountain which is vertical is infinite, right? So these are regions where the slope is infinite. So how do we incorporate infinity into a graph? Okay. So are you able to understand what is the difficulty here? See, when we were dealing with continuous random variables, finding out when we are dealing with continuous random variables, finding out the density function was pretty easy, right? So this we easily found out this and this. Okay, so when we are dealing with discrete random variables, okay, we face difficulties at these points, right? Because the slope is infinity, so we don't have any method to represent infinity in a graph, right? So if we want to represent infinity along this y-axis, right, but we don't have any method yet. So till now, whatever we have learned in mathematics, we don't have any method to represent infinity along the y-axis. So we want to plot at each point, we want to plot some infinity values, but how to represent that infinity? So for that, what we do is we have introduced the function called an unit impulse function. Okay, so the lecture will now focus on what is known as the unit impulse function. Okay, so all these locations have infinite slopes. Okay, so what we do is we represent those infinite slopes by an arrow pointed towards the upward direction. Okay, and then we represent some values near the arrow which represent the height of that, not the height of that arrow, it represents the area under that arrow. Okay, so we'll see what is this unit impulse function in more detail in the next session. I think we are almost at the end of the session. Okay, I'll just give you a brief description of how to represent our density function. Okay, so this is actually density function. Okay, so this is our density function. Okay, so for the discrete random variable case, the density function is represented as a summation of probability of xi multiplied by a special function which is denoted by del of x minus xi. Okay, so this special function del of x is called the unit impulse function. Okay, so what is the unit impulse function? We'll see in more detail in the next session because we have come to the end of the session. Okay, so unit impulse function is represented graphically by this symbol. Okay, that is an upward pointed arrow, and it has some special properties, and its definitions are having some peculiar characteristics, okay, which we'll be seeing in the next session. Okay, so for now, just consider this: it is a summation of probabilities of the points xi multiplied by a unit impulse function. Okay, the density function is the result of this summation. Okay, so please wait for some time. I will take the attendance, and then you can move on to the next class. So we have introduced two new functions in this lecture. So hope you have understood this. If you have any queries, you can ask me in mail. Okay, and just take a snapshot of all. Okay, so today I'm seeing 62. Okay, with me it is saying 62. So total student number is 61, right? Yeah. Just a minute. I'll take snapshot of your attendance. So once I complete this, you can leave for the class. And just wait for some time. This. 33. Okay, I have taken the attendance. So hope you understood today's concept. So since many things are new to you, I think you can call me or you can message me if you have any doubts. Okay, so today's concepts are very new to you, so you can just give me a message or you can send me some mail. Like, what are your doubts? Okay, so I'll be available to clear the doubts anytime. Okay. Okay. So thank you all. You can leave for the next lecture.